I went out to Moffett. The Dunkball Foundation helps fund the summer intern program out there, which is fantastic. We're part of the Spark program, and while we were there, Dr. Smalley was one of the speakers that they had during the dinner. And I was so fascinated by what she had as an experience because she went through the Spark program out there. And so it's going to be interesting to have her tell you about what her experience was and also what's going on at Moffett. And on a private note, I was out at the McKinley campus for some minor surgery yesterday. And that place is fantastic. If you haven't gone down McKinley to see the new campus, the new hospital that Moffett has out there, it's truly amazing. We have just a world-class cancer center. And now I'll introduce Dr. Ina Smalley.
As Sandy mentioned, I wanted to share with you about my journey to where I am today as a scientist. I didn't always want to be a scientist. Actually, my first encounter with biomedical research actually occurred when I was quite small. When I was a teenager, I had a recurrence of a very rare but benign vascular tumor around my neck, and a lot of the doctors did not know what to do with it because it was a rare disease. There are not a lot of experts in the world who know how to manage it, and I kind of bounced from doctor to doctor trying to figure out what to do, and finally encountered a clinician scientist was actually one of those first faculty members that I approached who couldn't at the time take me on. And I ended up winning third place in that science competition. I thought, wow, maybe this is something I'm good at. Maybe this is something I could do. And so that semester I switched my major. I switched to biology. I applied for a SPARK internship at Moffitt, which is a sponsored summer internship. So which means you get paid for your time. It's a wonderful opportunity for them to really become fully immersed full time in research. And again, the mentorship I had and the experience I had was just so inspiring. I thought, I think I want to do a PhD. So when I completed my degree at USF, I signed up for the cancer biology PhD program at Moffitt. So, and again, throughout that experience, my mentorship team was so outstanding. They were advocating for me all the time. They were encouraging me. They were guiding me through difficult times. What people don't realize is, 95% of science are things going wrong. Things not going the way you expect, getting bad results, trying to optimize the way you do experiments, and then we all live for that 5% of the time. Something turns out great, we make a discovery, which is so brilliant. And, the mentorship I had through that time was just outstanding. They were advocating for me, they were networking me with other people who were important in the field, who were connecting me to the right technologies, to the right methods, to really grow my research forward. And it was an amazing experience. So, and at that time, I really fell in love with melanoma research. And that work focused on late-stage melanoma patients, so unresectable metastatic melanoma patients whose tumors were resistant to therapy, really complicated central nervous system metastases. And I thought, I love doing this. I want to make a difference for patients who don't have any therapeutic options right now. And I just really, really fell in love with it. And I thought, I love Moffitt. I love what I do here. I can't think of an experiment that I wanted to do that I couldn't do. So for my postdoctoral research, again, I stayed at Moffitt. And again, my mentorship team was amazing. Again, they really promoted my early success. They guided me to the things that I wanted to do and things that I should be doing if I wanted to continue to pursue my career in academic science. So they were telling me, based on their experience, what a successful scientist needs to do. So not just getting to the end of your kind of that stage of your career and thinking, okay, how do I take the next step? No, from the first step when you start that position, a good mentor will guide you and say, 5 years from now, this is what you're going to need to have. So let's start. Let's build a timeline of how you can achieve this. That was really, truly wonderful. And then, because of this amazing mentorship I had up until this point, I had a lot of early success in my career, and this actually allowed me to get a really prestigious grant from the National Health Institute to transition to become a faculty. And at this point, again, I had the opportunity to go to another top research center in the U.S., and again, I chose to stay at Moffitt. So you might be seeing a common theme here now, choosing Moffitt every time. So I had the opportunity to go to graduate school. I interviewed at different places, interviewed at Columbia, UF, other places in the U.S. And even for my postdoctoral fellowship, again, I had an opportunity to go out. And they always tell you in science that you should never stay at the same place. You should always go. So this was traditionally a poor career choice. But I am so thankful that I've done that. And so Moffitt has been an amazing facility. They really support all their scientists. They are always pushing for the cutting edge technologies to be available for us to be doing things that are relevant clinically. So those really close ties with the clinic, they don't have it in other places. Like when I interviewed at Columbia, I was really interested in translational science. I wanted to make an impact short term, really quickly for patients in the clinic, perhaps knowledge. And they're like, it's across the street, but we don't interact much. And that was kind of a common theme I had. So, and the other thing you might have noticed now is the mentorship that I've received. At every stage of my career so far, I have received superb mentorship. And so this really kind of just inspired me to stay in academic science and pursue this field. And I would say that it is the absolute key to my success so far. And it's allowed me to establish my own research group. I now have my own lab, my own team. And we study melanoma, late-stage melanoma. And one of the other things we study are leptomeningeal metastases. So this is when cancer spreads to the membranes that cover the brain and spinal cord. And the fluid, which is the cerebrospinal fluid that runs in between those membranes. So this is really like the space that is critical for neuronal function. It's critical to keep the central nervous system clean of toxins, provide the nutrients and everything that's needed for the brain. So it's an essential system. So when the tumor gets to this space, it is devastating. The majority of patients, it's a rare disease, it's a rare complication, but it happens in patients with many different tumor types. And at the moment, they do not have any therapeutic options. So typically, for example, if a patient were to get diagnosed today, their survival is, the prognosis is so poor that many of them will not make it to Christmas. So survival for these patients is measured in typically near weeks to a few months. So we've made so many advancements, for example, in metastatic melanoma. We have targeted therapies, we have immune therapies, we have cell-based therapies. None of these work at this specific site. So a patient could be responding in all other kinds of sites of disease, even deferment, but they will fail all therapies at this site. So my lab really studies what is unique about the tumor microenvironment in this space and the tumor in this space that allows it to survive. Typically, this environment should be inhospitable to a fast-growing tumor, but it's not. They thrive in that space, so we're trying to understand what drives this, and we're actually making great progress. We found that there's a specific metabolite that's elevated in this fluid of patients who have this disease, and we found that this usually actually occurs in metabolic disorders, inborn metabolic disorders. So, when babies are born and they do that blood spot test, they're testing for some of these metabolic disorders like the vagal circulatory disease. In this disease, this same metabolite, the branched-chain ketone acid, is also very elevated, and that leads to severe neurocognitive dysfunction. And this is also what we see in the patients with the cancer that spreads to this site. And we thought, well, there are FDA-approved therapies for these metabolic disorders. Could we maybe try to translate this to patients who have leptomeningeal disease? And we've already seen in some of our preclinical studies in our models that indeed, if we take this therapy and apply it to models of leptomeningeal disease, we can slow down the neurocognitive decline and we can improve immune therapies. So, there's potential to move this field forward, although it's been a very difficult field to study with the kind of resources we've had at Moffitt. We've been able to make small steps forward. So I'm really excited about our work and what we can do in this space. And so, I couldn't do any of this without a mentorship like that. And I just wanted to touch quickly about mentorship and what makes a good mentor. And in my experience, a mentor is not just a teacher. Sure, you teach, that's part of the job, but you're also the cheerleader, you're the advocate. You don't just show people how to do it, but you also, once they do it, you tell all your friends about how awesome they are at doing this. You tell everybody, watch out for this person. They're going to be the next big thing. And you help them become that. You inspire them. I was inspired by the mentors I have. It's not that just I came into science and thought it was the greatest thing. I came and thought this is difficult to do. And despite it being difficult to do, I was still excited realize this, but when you get a tan, when your skin tans, that's damage to your DNA, that's damage to your cells. You don't want that. So I encourage everybody between hours of 10 and 4 to try to stay out of direct sunlight. Use sunscreen, cover up. The best way to deal with insecure melanoma is to prevent it. And then, of course, early detection. Everybody here should be going to their dermatologist once a year. And if you don't have a dermatologist, Moffitt actually has a program called Mole Patrol. We host several screening events throughout the year at major, the raised baseball games. We do it at Pier 60 over the summer. So major events, look out for Mole Patrol from Moffitt, free cancer screening. It takes just a couple of minutes. You come up, they look you over, and they let you know if there's anything concerning. Once a year at least, everybody, and I'm especially looking at the men because you guys are really bad at going to your doctor. Do it. The second thing is Moffitt. I want you to know that the research that's going on there and especially the training programs that we have there are world class. They are worth supporting. They are worth advocating for. Wholeheartedly, especially this SPARK program, that really got my foot into science and really got me super excited about it. I can see the trainings that we have had this past year. They're excited about science. It's just infectious. And it's a great program. And then the third thing is be a mentor. If there is anybody, and anyone, it doesn't have to be in the science field, anybody can be a mentor. A single person can really only do so much to change the world, but if that person mentors 10 people, and if those people mentor 10 people, now you've got a 100-person army, kind of small army, working on the same thing to move something forward. So that's the biggest impact we have, and I feel so honored to be able to be in a position to be a mentor to others. It's the thing that I actually love the most about the job. So if somebody, a young person, somebody inexperienced, new to a field, knocks on your door, gives you a call, sends you a cold email, and says, hey, I'm new to this. Would you mind taking some time? Do it, make the time. That really makes an enormous difference. So that's it for me. I'd be happy to take some questions.
Ron's got his hand up.
Thank you, Dr. Smalley. That was very, very exhilarating the way you combine when not to go out in the sun and when you give your mentees a great day in the sun. I love your passion for your mentees. I went to the ballpark about 4 years ago to brain cancer, and I related to Mom and said, if you were to be going hypothetically this morning for a grant committee for, let's say, $1 million grant, what could you do you're not now doing that you would like to do in your research to earn an additional $1 million grant to go forward?
Absolutely, that's a wonderful question. So, as I mentioned, one of the things about mental disease is that it's been greatly understudied. And one of the challenges of it really because it's a very diffuse disease. It spreads out the entire kind of neurological system, your entire neuroaxis, and it's been hard to sample. Traditionally, we haven't been able to study it because it's not something that patients would go and have resected. And so we've actually finally found a way to get access to some of the tumor at this site. And there are new technological advances that now allow us to profile these small numbers of cells that we're able to gather from there. And there are two approaches. One approach allows us to look at the entire kind of transcriptional profile, which means what kind of signaling programs in biology are turned on in these cells that allow them to survive in this space. And the other technology actually allows us to look at this within the space of the tissue. So we can harvest the tissue from a patient and then look at all of these biological programs not only in the tumor but also in the tumor microenvironment, because we know that in normal cells in this tumor microenvironment, actually The only downside is that they're very expensive. So we have only been able to sample a small number of, or profile a small number of samples. So we can learn a little bit about the tumor in that way, but if we can profile a large cohort of samples, we can really see what's patient specific and what is specific to the disease and what can be translated to other types of meningeal disease. So not just from melanoma, but from breast cancer, from lung cancer, from leukemias and lymphomas. So I would say that the biggest place in the studies that we do where we can really utilize the money is applying some of these really cutting-edge technologies to these tumors so we can have a deeper understanding of what's actually happening in that space and how that's different from other tumor cells.
Good morning. Thank you for sharing with us. I'm Ashley Teeling. I'm a CPA by trade, but I also could have maybe pursued engineering or medicine. I chose not to. I spent 2 summers at Moffitt in the anesthesiology department. The early biomarking of postoperative nausea and vomiting, whether we could detect the 35% that would not make it to the other side without throwing up. But the reason I stood up today to ask a question is now, fast forward 15 years later, having pursued something different, but still with an interest for research and science and those impacted with cancer. There's a condition, I don't know if you're familiar with, paraneoplastic syndrome. So in the foundation that we work with Moffitt through Dr. Martari in that department, we are actually trying to shut down sort of the permeability of the blood-brain barrier in the way that the immune system is attacking in some cases, the cerebellum and PCD. So has anyone within the institution and within the clinic and what have you given any thought to, in this particular set of circumstances, patients with cancer, particularly small cell lung cancer, breast cancer, perhaps testicular, uterine, ovarian cancer, we don't want that. We don't want that attack. Is there a way, maybe through immunotherapy and things like that, to maybe trigger that pathway so that in an instance of, and I'm not going to get this right, but leptomeningeal disease that's impacting your melanoma population, is there anything you can see there, any collaboration, perhaps, and perhaps maybe some funding to go with it?
So that's a wonderful question. So the question is, if I understood right, in the space, is anybody doing anything in the space of studying the blood-brain barrier permeability? And is there anything that we can do to kind of modulate this permeability? So for those of you who are not familiar, the blood-brain barrier is really, it's set up so that your brain is not is protected from your own immune system, so you don't get like kind of autoimmune effects in the brain because it's a lot more sensitive to perturbations, and because it's integral to your function and being alive, you don't want those kind of really big bursts of immune responses. It also keeps pathogens, so bacteria and viruses that are maybe systemic, from penetrating into the brain, because that's kind of the last frontier. We want to protect that system as much as possible. And there are many challenges to modulating the blood-brain barrier in cancer research. So on one side, for example, with brain metastases and leptomeningeal metastases, oftentimes you would have this disease which permeates the blood-brain barrier. So basically, this is barrier. It affects the integrity of the barrier, breaks it down. In some ways, that's bad because it affects the normal neuronal function of that system, but in some ways, it's good because patients who receive systemic therapies can now benefit in the brain because the blood-brain barrier not only keeps pathogens out, but it can also keep drugs out. So in some cases, it's very important for therapies to reach the brain. And in other cases, for example, with the paraneoplastic syndrome actually interested in studying the blood-brain barrier, we do, there are a couple of other labs in the institution that are really looking at studying how, these tight junctions in the vasculature of the brain, how they function. Your question is really difficult to answer directly. We don't know for sure all the players and molecular players that mediate the blood-brain barrier, and it's actually different depending on the context of the tumor type and the kind of the syndrome we're having. So whether it be brain metastases or perineoplastic syndrome, I imagine that these are very context dependent. So we have to set a model specific for each one to look at that. But there's definitely a lot of interest in that space. There's definitely a lot to do in that space. And I know there are investigators at Moffitt who are very interested in looking at that. So definitely, if anybody feels like they are working outside of the scientific field but are interested in becoming involved, think that maybe there's something in your field that you can contribute. I mean, we do all kinds of projects. We collaborate with engineering departments. We collaborate with math departments looking at mathematical modeling. Great ideas come from unconventional collaboration. So we do have opportunities where people can come in and engage with the science. So we have our yearly Moffitt Scientific Symposium. Come down, take a look at what we do. See if there's something that sparks your interest, maybe something you can contribute to, or come up with a great new idea of how to approach a question that hasn't been answered yet. So I know this doesn't directly answer what modulates this blood-brain barrier, but there is a lot of research going on that space, and definitely people who are interested in learning more about it. In fact, we're setting up some models actually of being able to model this blood-brain barrier in a tissue culture dish. So you can actually set up where you take the different types of cells and layer them the same way that you would have in the blood-brain barrier, and then study how the permeability is affected by looking at like the electrical connectivity through it. And so you can put different drugs on, you can put additional cells on, you can put tumor on, and see how that membrane is affected. So it's definitely something that can be studied.
My name is Mark Proctor, and I spent the worst day and best day of my life at Moffitt. January of 2019, I was diagnosed with pancreatic cancer, and I researched it that it was a 4% chance of survival. January of 2020, I was diagnosed cancer-free and have been since then. So I owe a lot to Moffitt and the process of detection and procedure. But I became fascinated with one part of the detection process, and that's the markers. So I had in the pancreatic cancer CA19-9, and I was over the range. So I talked to a number of oncologists, and I said, can we do an early detection of doing this tumor marker test to find out if you predilection toward that particular cancer? Now, privately, you can get tests done, but it's very expensive, and insurance will cover. So, kind of like a general idea of what type of research you're doing to prove that it may be a predictor of potential cancer.
That's a wonderful question. So basically, there are of course challenges in early detection, and as I said, one of the main, the best things about treating cancer is prevention and early detection. And there is definitely a lot of work being done in that space. And as you mentioned, not a whole lot of it is currently applied to the clinical practice because it's still kind of early on, it's still expensive. Insurance companies still don't cover it. It's not considered something that is essential yet. And this is why one of the other things that I think is super important moving that forward is patient advocacy and advocacy in general. we've been applying that to the cerebrospinal fluid, and we actually have a patent out on this to see if we can use that for diagnostic purposes. And the reason we went with that system is because it's already CLIA certified to be used in a clinic. It's already approved to be used for diagnostic purposes, but in the blood. So it would be easy to translate that to other purposes like cerebrospinal fluid. But really, what we need are more advocates, both scientists, patients, anybody really, to tell the funding agencies, to tell our leadership that this is important and this is where we want to invest our money. So that's the biggest thing. From a scientific perspective, I'm always advocating for any research that focuses on prevention and early detection. But we need the funding agencies to also say that this is important and put the money, towards that. So they're definitely, I don't work on this personally, but I know there are many other groups working on pancreatic cancer early detection, colorectal cancer early detection. There are many cancers that can be detected early. There are also many cancers that really do have early screening approaches. So, for example, breast cancer, as I mentioned, skin cancer, even colorectal cancer, there are things you can do, colonoscopy, there are kits. And everybody, just as you should be getting a yearly skin exam, if there's any early detection cancer approach that you have the access to, do it. So colonoscopies are one example, and it's very important to do those.
Good morning, Dr. I'm Judge James Curry. I couldn't tell you how many friends, family that I've lost. And I couldn't tell you how many at young ages. And I couldn't tell you how many have been diagnosed cancer. So I know that cases aren't rare. I thank you for doing the work that you do. In my courtroom, we don't see a lot of cancer research scientists. I'm also a father of 5 children, and I'm wondering, not everyone grows up to be a research scientist. And I'm wondering if you might have any advice to young children on what they can do to make them grow up to be people who make a difference in people's lives and make the world a better place.
That's a wonderful question. I would say that the biggest thing that young people can do to make a difference in the world is, one, identify something, a problem, a gap in knowledge, anything you think that hasn't been answered that you would be really passionate about. So something that you can really see yourself dedicating your entire life to. So, cancer research, it's not a 9-to-5 job. It's something, I do cancer research at work, I go home, I do cancer research at home, I think about it, I think about the patients, I think about the scientific problems, I'm troubleshooting experiments as I'm falling asleep. It's, something I'm thinking about on the weekends, we go to conferences on the weekends, we share science, so it's something that I found that it's not, I don't do it 9 to 5, it's an entire dedication of your life. So I would say for young people to, one, open yourself up to exploring as many different career options as possible. Shadow people that you know in their careers. Even if you're not sure that you would be interested in that, just go for a day and see how it is. You, just by experiencing different things, you will find your passion, you will find the things that are exciting to you, and most importantly, you're going to find that mentor, that teacher that will inspire you to go further. And so, I think mentors are really the things that guided my career for the most part. I always became attracted to things that came with a good mentor. So, the biggest thing they can do is just explore as many different opportunities as they can. If somebody says, hey, I'm doing something novel, and they say, the thought I had at the end of it was, but the kind of impact this person had in my life, they probably don't even quite grasp how much of an impact. They probably don't even know that I'm thinking about them right now. And like, it's impacted my entire life. And then I thought, what if I could be that person for somebody? Like, you know, if I can impact the lives of, you know, a single person in this kind of way, that would be so fulfilling. And so that's kind of what drove me that way. So I would say the biggest thing young people need to do is find a mentor that would make you want to do what you do 24/7. Not that you have to do it 24/7, but somebody would really inspire you to want to do those things. And someone who would inspire you to do things that help, mostly benefit others.
I'm John Masters. First, I'd like to thank you. As a non-scientist, I think I understood most of what you said today. I appreciate it. My question is, it sounds like your field of study might be somewhat narrow, and you alluded to funding agencies. Does that make it more difficult to get funds?
Yes and no. So in some ways, so I talked about the meningeal disease a lot. It's definitely one of the major programs that we have. But there's probably me and two other groups in the entire world that are working on this problem. And there are, you know, if we consider all cancers, probably for metastatic cancers, up to 10% of them will end up in the meningeal space. Oftentimes we don't diagnose it, but if we could do autopsy on everybody who died of cancer, we would see evidence of this disease in probably a quarter of the people. So now, and as we are improving other therapies for cancers and metastatic disease, we're actually seeing an increase in meningeal disease. So it's a problem that's going to become more of a problem as we get better at treating cancer. So because we know almost nothing about this disease, and there are almost nobody studying it from some perspective, yes, it's kind of low-hanging fruit, and they want to sponsor because they want somebody to be working in that space. But from another perspective, yes, it's a very specialized field. And obviously, unless you can get somebody excited about meningeal disease, they care less about it. So yeah, that is also a challenge in some space. But what we always try to kind of convey in our funding applications is, although this project is specific for meningeal disease, it might impact many other diseases and processes. For example, as was brought up earlier, the blood-brain barrier. If we can understand how the tumors, you know, permeate the blood-brain barrier to get into that space to begin with, we'll understand that process for many other cancers. We'll also understand how to reverse that process when therapies permeate the blood-brain barrier, and we want to stop that from happening. So, you know, even in the most narrow scientific fields, you can make discoveries that impact a huge population of people. And most of the time that happens accidentally, I would say.
My name is Bill Lazarus. I've been doing predictive analytics for 30 years. And a colleague of mine actually came up with an algorithm that was highly predictive of uterine cancer. It was entirely disregarded by the scientific community because he had no idea of the causal path why it predicted it. And because they couldn't say what was going on, because these models are frequently very black box models. But that was predicted. It was completely disregarded. Now, this is a while ago, before deep learning became so prevalent. So I'm wondering what's going on at Moffitt in terms of using deep learning on an unsupervised basis to try to understand markers, because you have so much data. And looking at it just clinically and
curious as to the push at Moffitt specifically and in cancer research more generally to employ these deeply ununderstandable techniques to identify things that are understood. It's deep pattern recognition, and you never really understand what the pattern is.
That's a wonderful question. So for those of you who don't know, deep learning, machine learning, and artificial intelligence, this is basically applying these computational techniques to be able to process and detect things that maybe would either take a really long time or, a specialist to do, or something a single person wouldn't be able to do, but a machine can process, thousands of tissues, millions of tissues. So we actually do have a huge effort in machine learning and artificial intelligence at Moffitt. We actually started a new department on this. We have a department chair who's been around for, I think, almost 2 years now, and is actively recruiting faculty in that space and trainees. We are looking at, there are many projects in this space. Specifically, we're trying to see, for one example, when you get a biopsy of any kind, you have a suspected tumor, traditionally they will take a sample of the tumor and then a pathologist will look at it under the microscope. And people are not infallible. Many times pathologists will detect it, sometimes maybe they do not. And the idea is, if we can teach a computer to detect tumor much better than a person, we could potentially utilize this. Not only will it be more cost effective, it would be faster, it could potentially, it can learn on such much bigger data sets than a human can. So it could potentially provide an advantage for early diagnosis and maybe the diagnosis of disease that's typically difficult to diagnose. So yeah, there are definitely a lot of development in that space at Moffitt. It's something we're doing. I know a project on one of our T32 sponsored training programs for postdoctoral fellows. They're looking at applying deep learning to detecting early stage lung cancer. So going from dysplasia to stage 1. So there's definitely a lot of work going on in that, and Mark is very excited about that space. So and we're trying to also apply those not just to diagnosis, but also to clinical practice. So, for example, consultancy. So when you want a second, third opinion, and you have a clinician reviewing the charts to determine, okay, is this therapy that has been recommended, is that the best therapy for the patient based on their genetic background and whatnot? A machine could do this. A machine could probably do this in a more thorough, deeper kind of way. So that's also another space that Moffitt is exploring.
One last quick question.
Rosemary Anderson, thank you so much for being here. I especially appreciate you encouraging all of us to be mentors in whatever field we might be able to help others. So thank you for that. I'm not only cancer survivor here, or breast cancer survivor, but I guess my question is, and you may have mentioned this, about hearing aid matters to people a while ago, so I missed something. But old age is secondary hearing. On diet, is anything about kind of what that is?
So there is actually a lot of work going on diet and nutrition and how that impacts cancer development, cancer growth, the effectiveness of therapies, patient outcomes. We're even looking at diet. So as I mentioned, for leptomeningeal disease with this upregulated metabolite, basically this happens because there is some disruption in the normal metabolic processes, and
you come back again and continue to enlighten us. It's very informative. Thank you.
Thank you very much.
It's the board of